We get started. Okay. So last time we proved Penrose's theorem about black holes. And in particular, we showed that if W is a trapped surface in a spacetime M, then M is not geodesically complete. And more specifically, we showed that some null geodesic from W, some orthogonal null geodesic from M ends. We could predict how far it can go before it ends, at least in affine parameter. So this is interesting, and it shows that when you have a trapped surface, some kind of bad behavior of the classical Einstein equations is unavoidable. But it really doesn't give us very much information about what there is inside a black hole. So if we think about the motivating example, the motivating example was this one, where the trapped surface corresponds to a point behind the horizon. And in that case, in the solutions we understand, every null geodesic, orthogonal, well, actually every causal geodesic, but in particular every orthogonal null geodesic from W ends after a finite affine parameter. And they all end at a singularity. So what's true in the motivating example is way more than Penrose actually proved. And to this day, the nature of what's happening behind the horizon of a black hole in general is really not well understood. I'm not planning to talk about the Kerr solution in this course, but if you've ever read about the Kerr solution, you know that what happens behind the horizon there is rather strange and quite different from Schwarzschild. And what's the generic behavior is really not that well understood. But anyway, whatever the generic behavior is, that question is not answered by Penrose's theorem. However, there's a nice surprise. Although Penrose's theorem didn't tell us much about what there is behind the horizon of a black hole, the same methods give a nice qualitative picture of black holes as seen from outside. So, well, this springs from the work of Penrose, but it was largely developed by Hawking, largely using some of the methods that Penrose had pioneered in the proof of the theorem that we explained on Thursday. Well, what I've said here is slightly oversimplified. This is true if we make one assumption. This is a very important qualitative assumption that was introduced by Penrose, who called it cosmic censorship. The idea of cosmic censorship is that you have to assume that nothing happens that's worse than a black hole. Well, what would I mean by worse? A black hole, at least if we trust the idealized Schwarzschild or Kerr solution, is there's a region of space where the Einstein equations break down at a singularity, say in the Schwarzschild solution. But if you stay outside, life goes on. And you can carry on forever as long as you stay outside the black hole. So something worse would be something that would prevent life from going on, even for a distant observer. Now, how would that happen? Well, the Einstein equations are highly nonlinear differential equations. They're called hyperbolic equations modulo the gauge group. And if you specify initial data on some Cauchy hypersurface, general theorems ensure that the solution will evolve at least for a while. But there's no general theorem about long-time evolution of the Einstein equations. In fact, a naive statement would be false because singularities do form, as seen in the case of the Schwarzschild solution. Penrose's idea was that the Schwarzschild solution isn't so bad because although there's a singularity, there's a cosmic sensor that keeps us from seeing it from outside. So worse than a black hole would be a naked singularity. Well, this is Penrose's terminology. So his original formulation was a little bit naive. In Penrose's original formulation, a naked singularity was a singularity that an observer can see. The trouble with that formulation is that once a singularity forms, here's an initial value surface, here's a singularity. Once a singularity develops, it's not clear what sense the Einstein equations make. So potentially, the future of the singularity is missing. So, you see, if that was to happen, then Penrose's original formulation wouldn't apply because there'd be no observer that can see the singularity. We solve the space-time for as long as we can. It's incomplete, like the Schwarzschild solution, and there's nobody who sees the singularity, because if you stay in the part of space-time that does exist, where you can solve the Einstein equations, you're always causally separated from the singularity. So Penrose's original formulation that nobody can see a singularity doesn't fully capture the intuition. So the modern formulation of cosmic censorship is more like the following. And possibly this is Garach and Horowitz. So first of all, we assume an asymptotically flat spacetime. That means asymptotic to Minkowski space. To Minkowski space. And then the claim is that the evolution from any Cauchy hypersurface that's asymptotically flat well, when I say the evolution, I always mean the hyperbolic evolution. You evolve using the Einstein equations for as far as you can go, getting a globally hyperbolic spacetime. So I always assume that M is globally hyperbolic. Then the modern statement of cosmic censorship is that the evolution of S is complete at infinity. So, I want to say this informally. It's complete at big distances for all times. What it means is that we can assume, no matter what happens in the interior of the spacetime, we can assume that, as in Schwarzschild, we could sit outside all the commotion and nonlinearities in a region where the Einstein equations almost reduce to their linearized version, and space-time is almost Minkowski space. So the modern formulation of cosmic censorship for an asymptotically flat spacetime just says that there are observers who live in a world that looks a lot like Minkowski space at spatial infinity, and they live there happily for all times. And we can study the spacetime from the point of view of such an observer. So that formulation excludes this hypothesis that the equations develop a singularity and nothing to the future of that exists. Because unless you constantly accelerate to the speed of light so that you can keep ahead of a light wave, right? Any reasonable observer who isn't constantly accelerating will eventually be in the future of this event. Now, cosmic censorship is unproved. I spent most of, for a couple of decades. Well, first of all, I felt there was very little evidence for it, and secondly, I hoped it was false. I hoped it was catastrophically false, not just false. Because what cosmic censorship prevents is a singularity where classical general relativity breaks down, and you would learn what happens instead. So, you see, I wanted there to be some distant event in the universe where the Einstein equations would break down. Then I wanted this version of cosmic censorship to be false. I wanted us to be here more or less at rest. And eventually we'd reach the causal future of this bad event, and we'd see what happens when classical general relativity breaks down. So for a couple of decades, that seemed to me like a loophole in claims that the effects of quantum gravity are very hard to observe. But regrettably, it's become difficult to claim. Well, regrettably, the evidence for cosmic censorship has become convincing in the last 15 or so years. To me, primarily from numerical simulations. So numerical simulations of black hole collisions have shown that apparently, even with rather extreme black hole collisions, classical general relativity doesn't break down. Cosmic censorship is valid in black hole collisions. People have been able to solve numerically for the outcome of a black hole collision. Of course, by now we've also observed black hole collisions observationally. That's extremely important for physics, but as a test of the mathematical assertion that cosmic censorship is true in general relativity, to me the computer simulations are more on point. The observations test a mixture of whether cosmic censorship is true and whether general relativity is correct in the real world. I feel like the observations test a mixture of general relativity and whether cosmic censorship is true in general relativity. But the simulations directly test cosmic censorship in general relativity. Anyway, by now, it seems very likely that cosmic censorship is true, but people who work on cosmic censorship from a rigorous point of view are not close to a proof. And it's widely considered to be the most significant unsolved problem in classical general relativity. So any questions on any of that? Yes?
Could you just clarify what you mean by asymptotically flat in the context of having, for example, an FRW cosmology?
Oh, FRW is not asymptotically flat.
Right.
I've stated this for asymptotically flat. We could state an analog for FRW. I won't. I'll let you imagine it for yourself. I've explained what the intuition is in the statements. And given that intuition, you should be able to adapt the statements for FRW. Likewise, the statements can be adapted for asymptotically ADS spacetimes. But I'll leave it as an exercise to think about that. So now we make two assumptions. We assume cosmic censorship and global hyperbolicity. Well, really, we make three assumptions. And we need an assumption about what's going on at infinity, which we'll take to be asymptotic flatness. By the way, I'm not describing, what I've described is sometimes called weak cosmic censorship, although the name is a little bit misleading. What I've described, I think, is physically the important version of cosmic censorship. Penrose also stated what was called strong cosmic censorship. It's got a completely different flavor, despite the fact that its name sounds like it's a strengthening of what I've told you. Well, I don't want to say more about that. Okay, we assumed asymptotic flatness or something similar. So it could be FRW, but we assume something that enables us to discuss the observations of an observer who stays outside the mass at infinity. So cosmic censorship tells us that we can ask what would be seen by a world line with a time-like, by an observer on a time-like trajectory at infinity. And we want to think of an observer who's more or less at rest. The observer might accelerate a little bit, but not drastically. So, an important definition is this. The black hole region is the part of space-time that the observer can't see. So again, in the motivating example of Schwarzschild, if this could be the time-like world line of the observer, and what the observer can't see is precisely the horizon and what's behind it. Now, okay. So, to state this a little formally, well, we've talked 100 times about okay, we let J minus be the causal past of the observer. That means all points that the observer can see. Instead of saying that all points an observer on I can see, I'll just say that all points that I can see. So a point is in the causal past of I. So if gamma is a causal path, so there exists a causal path from Q to I is equivalent to Q being in the causal past of I. So a fancy way to describe the black hole region is that the black hole region is all of M with the causal past of the observer removed. This symbol means remove. So A slash B is A with B removed. The first basic fact is that the causal past of a set is open, so therefore the black hole region is closed. Sorry, I shouldn't say the causal set of, sorry. It's not the case that the causal past of any set is open. I should say the causal past of this type of world line I is open. And that's because suppose from Q you can communicate to I. Then from slightly to the future of Q, you could communicate with I slightly to the future. The argument is similar to what I've said multiple times. Well, one causal trajectory starts at Q. The other causal trajectory starts a little bit later from the same point in space-time, but it just tags along behind the first one wherever it goes and arrives at the same place a little bit later. So if you can reach I from Q, you can reach I a little later from Q prime, and therefore any place in the past of Q prime is a place from which you could communicate to I. But if Q prime is slightly to the future of Q, then the past of Q prime includes an open set around Q. So if you can communicate with the observer from Q, you can communicate with the observer from any place in a small open neighborhood of Q. That's a simple but extremely important point. So since it is important, I want to stop in case anyone wants to ask a question about it. So our first result about the black hole region is that the black hole region is closed. And therefore, it will make sense to discuss its boundary, which we will after a little while. But we should also discover that it's non-empty. And any trapped surface W is in the black hole region. So we'll prove that in a moment, and as you'll see, the proof involves more or less the same ideas as in Penrose's theorem, but in a way, what it teaches us is more interesting, at least if you're an outside observer, than what Penrose proved in his theorem. Penrose proved that one causal curve from a trapped surface W meets an unfortunate end of some kind. It doesn't go on forever. Here, we're not going to prove that any of those curves end, but we'll prove that none of them ever get to infinity. So if you're making an observation at infinity, that's a much more relevant statement. So it's really this statement that says that the formation of black holes is generic. Okay, why do I say that? Let's go back to the idealized Schwarzschild solution. A point in the picture represents a trapped surface. It being a trapped surface is defined by some inequalities. If you change the initial data just a little bit, those inequalities are still satisfied, and there's a nearby trapped surface. So Penrose's theorem applies, and at least one geodesic from W doesn't escape, ends after a bounded affine parameter. So what we said Thursday applies, but also what we're saying today applies. We're about to prove that no signal can escape to infinity from a trapped surface. And therefore, that's the result that tells us that a small perturbation of Schwarzschild is still a black hole. It's not an unconditional proof, though, because we will be assuming cosmic censorship. The proof is based on asking what this observer I would see. And without cosmic censorship, we wouldn't know that that observer I exists. So that's why I'd say the correct statement is that you prove that the formation of black holes is generic in general relativity if you know that nothing worse is going to happen. So how are we going to prove that? So here's our compact surface. And I want to prove that from a compact surface, you can't communicate or send a signal to an observer on the time-like world line I at infinity. And remember, we'll use the fact that this world line can be arbitrarily far away. Well, suppose that there is a causal curve from W to I. I've drawn it as a dotted line because we're trying to prove it doesn't exist. It reaches I at some point P. Well, remember that spaces of causal curves from W are compact. So if there is any causal curve from W to I, there's one that gets there as soon as possible. In other words, if I measure the proper time along this path, if such a gamma exists, there is a gamma that minimizes tau. Tau is just a time parameter along I. We could take it as the proper time of the observer, but all that's important is that it's a function that increases along the observer trajectory. So we're exploring the following situation. W is a trapped surface. I is the world line of an observer at infinity. we're trying to prove that any trap, W is a compact trap surface. We're trying to prove that a compact trap surface is in the black hole region and can send a signal to the observer at infinity. If there is a causal path from W to infinity, then because spaces of causal paths in a globally hyperbolic spacetime are compact, a continuous function on the space of causal paths would have a minimum. Such a function is the time at which the signal arrives on I. And therefore, if there's any gamma, there's one that arrives as soon as possible. That's a typical statement that requires global hyperbolicity. If we removed a point from the spacetime that's on the optimal gamma, then there wouldn't be an optimal gamma anymore, and spacetime wouldn't be globally hyperbolic. So such a gamma is prompt. If there was a curve even better than gamma, you could have arrived sooner. So the one that arrives as soon as possible is prompt. Therefore, gamma is an orthogonal null geodesic. But that's not enough. The segment of gamma that goes from W to I has to have no focal point. But here's where we run into a contradiction. We know that since W is a compact trap surface, there's an upper bound on the affine parameter before the first focal points. And since W is compact, there's a fixed upper bound that's valid for all the orthogonal null geodesics. I, on the other hand, could be arbitrarily far away in the asymptotically flat region. So I could be beyond reach of all the segments of the prompt segments of all the orthogonal null geodesics. So there's no such gamma if I is sufficiently far away. So as I've indicated, this more than Penrose's theorem is really the result that says that black holes are generic in general relativity. But it's not an unconditional result. It depends on the cosmic censorship hypothesis. It really tells us that in general relativity, it's generic to either have black holes or some more catastrophic breakdown. Any questions? Yes?
Well, we haven't shown that whatever distance from this trap surface is the same for all the trap surfaces within the horizon.
Well, it's a compact surface. And as in the proof of Penrose's theorem, remember, theta is everywhere negative and is a continuous function on the trap surface. It's everywhere negative, so it's strictly less than some minus W for some constant. The argument for the question that was asked was, the distance, the affine parameter distance to a focal point, could it be different for every point on W?
Sorry, I misspoke. What I meant was that, so this says that there's some horizon for W.
Yes?
It doesn't necessarily show that every trap surface within the black hole has that same boundary, right?
Well, we'll analyze what's the boundary. We'll analyze the boundary of the black hole region in about 10-15 minutes, I think. But what this shows is that from any given compact trap surface, you can't communicate to infinity. Yes?
Is that what you just said true regardless of whether we're in an asymptotically flat spacetime? Like
No. The de Sitter example shows that compact.
That, like it's causally disconnected from scribe plus.
What's that?
That the trap surface is causally disconnected from scribe plus.
Well, the de Sitter example shows that in that case you can communicate to every time-like trajectory from a trap surface. So we gave at the end last time, and I'm sorry it was a bit of a rush, we discussed de Sitter space, which doesn't satisfy the hypotheses of Penrose's theorem because to make it globally hyperbolic, you need a trapped initial phase surface. It's a closed universe. Okay. a point down here represents a trapped surface from which you can communicate to any time-like trajectory. So in de Sitter space, nothing like what we've said is true. So what we've said is a result, I've stated it for asymptotically flat spacetimes, you can adapt it to FRW and also to asymptotically anti-de Sitter. But this result the statement identifies a class of observers at infinity who can't see the trapped surface. So we're going to need to have a notion of infinity to be able to make such a statement. Yes?
How generic do you expect trapped surface to be in space-time?
Well, you see, the condition for a surface to be trapped is what's called an open condition. It's defined by inequalities. So if you take any space-time, then any space-time which is sufficiently close to that one also has any space-time with a trapped surface, any sufficiently small perturbation will give a nearby space-time that also has a trapped surface. So that was why Penrose introduced the notion of trapped surfaces, and I should have stressed that more on Thursday. So the ideal Schwarzschild case, you just solve the equations. He wanted to get a similar behavior without spherical symmetry. So he abstracted from Schwarzschild the notion of a trapped surface and observed that anything sufficiently similar to Schwarzschild, even if not spherically symmetric, has a trapped surface. And so that was the motivation for the theorem he proved that we discussed Thursday. And similarly, it's the motivation for the statements we're discussing today. Any other questions?
So where did we use cosmic censorship in this argument?
We use the fact that there's an observer at infinity whose experiences we could discuss. So if something bad happened here and the space-time didn't exist to the future of it, then this observer's experience comes to an end. We can't discuss what that observer will see in the far future.
In this example of the negative singularity, don't we also have observers whose experiences we've discussed, the ones that are accelerating?
Maybe, but then we have to, well, see, if in this story though, if you accelerate so fast that you can outrun a light ray, then this argument won't work. Do you see the problem? So, yes, in this example where the space-time doesn't exist to the future of this point, there are time-like observers. Say an observer with constant acceleration can outrun a light ray, and the cataclysm that emerged from this point never reaches that observer. But by the same logic, the light ray emanating from W wouldn't reach, well, you wouldn't learn anything from the fact that a light ray emanating from W doesn't reach that observer. If you have an observer who can outrun light rays, even in Minkowski space, there would be regions that observer can't see. It would be a statement about the observer, not about the space-time. Any other questions? Well, so here's our initial value surface S, and here's a trapped surface W. So one would intuitively believe that if you can't communicate with infinity from W, it's even worse from inside W. So W is, let's say, the boundary of Q, where Q is also contained in the trapped surface. Q is compact. So W would be the boundary of either its interior or its exterior, but only its interior is compact in an asymptotically flat spacetime. So intuitively, so if there's no causal curve from W to the observer at infinity, we'd expect that there's no causal curve from Q to infinity. So that's true, but part of it is a homework problem, so I'm not going to completely explain it. I remind you, you can find the second homework assignment either on my website or else on Canvas. What you'll prove, one way to say what you'll prove in homework is that the boundary of the future of Q is Q union part of the boundary of the future of W. Another way to say it is that a prompt null geodesic, a prompt causal curve, let's say, I should say, since we allow a single point as a causal curve, I really want here a non-trivial causal curve that consists of more than one point, actually comes from the boundary of Q, which is W. So that statement is actually, I think, problem 2 in the homework, and it's supposed to be an easy exercise if you bear in mind everything we've said. But since it is on the homework, I won't prove it. But if you know that that's true, then it's clear that if you can't communicate with the observer at infinity from W, then starting in the interior is no better. Because if you could communicate, there'd be a prompt causal path of communication, and that would actually be a path from W, which we just proved didn't exist. So we can fill in the picture a little bit. Not only is a trapped surface in the black hole region, but its interior is as well. And of course, interior is a slightly vague notion because there isn't a canonical initial value hypersurface in general relativity. So when we say the interior of W, we really would mean the domain of dependence. Let me try to give another picture. Here's W, which I'm drawing as a circle, and its domain of dependence would be all points with the property that a causal curve through that point. We could pick a particular Q on some hypersurface, on some S. On some S, the interior of Q, on some S, the interior of W would be what I called Q. But we could bend S toward the future or the past. So the argument applies equally well to any Q that we would get by bending W to the future or the past, by bending S, the hypersurface, to the future or the past, still requiring it to pass through W. And that way we'd fill out what's called the domain of dependence of any one of these Qs. We can't go farther than that in the past, but we can go farther than that in the future. You see, a more trivial argument shows that the future of Q, so once we know that Q is in the black hole region, it follows that the causal future of Q is also in the black hole region. That's true kind of trivially. Here's Q. We assume that we know that from Q you can't communicate to I. Here's a point in the future of Q. If you could communicate to I from P, then you could do so from Q, because by definition, P was in the future of Q. So this first path, gamma 1, exists. If the second path, gamma 2, existed, we'd have gamma 2 composed with gamma 1 from Q to I. So the future of Q and also its past domain of dependence are in the black hole region. Now, black holes can merge, which physically is clear. If you can have black holes, they can orbit each other gravitationally, spiral in, emitting gravitational waves, and eventually merge. And in fact, by now we've observed that experimentally with LIGO. But black holes can't split. So, what would it mean to say that a black hole can split? Well, first of all, okay. So, I'm drawing the black hole region on an initial value hypersurface. It's a closed set, but it might not be connected. Each connected component of the black hole set is a black hole. So, the number of black holes on this hypersurface is just the number of black holes. Well, is the number of connected components of the black hole region. So I've drawn an example where on the surface S there are 3 black holes. Now, we could have a later Cauchy hypersurface S prime, and the number of black holes could be different. It could be either bigger or less. New black holes could form, but old black holes could merge. The number of black holes on S prime can't be 0. That's because any future going causal curve from the black hole region has to reach S prime, since S prime is a Cauchy hypersurface. And since the points where that happens are in the future of the black hole region, they are themselves in the black hole region. So there has to always be a non-empty black hole region on S prime, but it could be connected even if the black hole region was disconnected on S. That would happen if all the black holes that were initially present merged. However, let's prove that black holes can't split. To make the picture simpler to explain, I'll assume that initially there was only one black hole, and we'll discuss whether it could split into 2. So initially we have a single black hole filling out a region Z of space, and on the later hypersurface there are 2 black holes. So first of all, that is a possible situation. It will happen. Z minds its business and ends up as either Z1 or Z2, and meanwhile a second black hole forms. So this can happen. But we want to prove that the only way this can happen is what I just said, that Z goes to either Z1 or Z2 and the other black hole somehow formed. So what we want to show didn't happen is for Z to split into 2 pieces. So the proof is as follows. Consider future-going causal geodesics from Z. So, well, I prove that Z is compact, the black hole region. Sorry, I prove that Z is closed, but I should stress that since we're assuming asymptotic flatness, we're assuming the black hole region doesn't extend to infinity. So Z is actually compact. And given this, the space of future-going causal geodesics from Z is also compact. This wouldn't be true if we said future-going time-like geodesics. A time-like geodesic could be very, very close to light-like and has no limit. So the set of time-like geodesics from Z would not be compact. But the set of causal geodesics is compact. Since Z itself is compact, if you had a sequence of such geodesics, the initial point on Z would, for some subsequence, would converge. And then the directions you can go are just directions in the future light cone from that point. But the space of directions in the future light cone, including its boundary, is a compact set also. So the data that would determine a causal geodesic from Z, namely an initial point and an initial future-going causal direction, that's a compact set of data. So the set of causal geodesics from Z is compact and connected. It's connected because the data are connected. The data are a point in Z, which we assumed is connected, and an initial causal direction, which is also connected. So now, solving the geodesic equation gives us a map from Z to the black hole region. We're just solving an ordinary differential equation to find the geodesic. And as we've observed several times in this course, the solutions of an ordinary differential equation depend smoothly on the initial data. So the space of these geodesics can't be split as those that go to Z1 union those that go to Z2. In other words, if we have a future-going geodesic from Z that goes to Z1, a nearby one goes nearby, and it can't suddenly jump to Z2. So the smoothness of the map from the initial point of a geodesic on S to the point it intersects on S prime implies that all the causal geodesics from Z have to go to the same component of the black hole set on S prime. For example, they might all go to Z1. So we've proved this argument proves no causal, all causal geodesics from Z go to Z1, not Z2. We want the stronger statement that there's no causal path of any kind, geodesic or not, from Z to Z2. Well, how do we prove that? Here we have to use global hyperbolicity. If there is a causal path, there will be one that minimizes the proper time, because spaces of causal paths in a globally hyperbolic spacetime are compact. If there is such a gamma, there's a gamma that minimizes the proper time. Because we're in a globally hyperbolic spacetime where spaces of causal paths are compact. And such a gamma will be a geodesic. But we've already proved that there's no causal geodesic from Z to Z2. So therefore, there's no causal path at all from Z to Z2. And we've proved that only Z1, not Z2, is in the future of Z. So in other words, we've proved that although black holes can merge, they can't split. Yes? Any questions? Thank you. Sorry. Thanks for the correction, Gustavo. Joaquin. Sorry. As we, I think, said in the first lecture, you can't minimize proper time in Lorentz signature. You have to maximize it. but a path that maximizes the proper time is a geodesic. By the way, in general, the maximum could be 0. So a causal path might be everywhere null. Then the proper time elapsed on that path is 0. But in any case, in a globally hyperbolic space-time, if there's a causal path between two compact sets, then there's one that maximizes the proper time. The maximum might be 0, but anyway, there will be one that maximizes the proper time, which will be a causal geodesic. Any other questions or comments? So if there aren't any more questions or comments, then I think we come next to the most important result, which is, well, okay, we'll head toward the most important result, which is the Hawking area theorem, but there are a few things to say first. So what's called the horizon is the boundary of the black hole region. So to be in the horizon means that you can't be seen from infinity, but you're arbitrarily close to points that can be seen from infinity. So, well, here's a sketch of the horizon. I'm drawing it as if it has a light-like boundary, and you'll see soon why that's the right way to draw it. We imagine Q as a point in the horizon. And then over here is our world line at infinity. Let me draw this in a way that will make the picture look a little more convincing. Now, saying that Q is in the boundary of the black hole region, not its interior, means that there are points very close to Q that are not in the black hole region. So we can assume there's a sequence of points, Q1, Q2. So the Qi are not in the black hole region, but the Qi approach Q. Now, by definition, the fact that the Qi are not in the black hole region means that from the Qi you can communicate with the observer at infinity. So there's a causal path gamma 1 from Q1, and there's a causal path gamma 2 from Q2. And there's a causal path gamma 3 from Q3, and so on. So we have causal paths from Qi to I. We're in a globally hyperbolic space-time, so this sequence has a convergent subsequence. So after passing possibly to a subsequence, we can assume that the gamma I converge to a causal path gamma from Q. I'll just call it gamma from Q. So, I'm trying to draw this thing a little bit thicker. That little bit of the horizon is meant to be the causal path that starts at Q, and is contained in the horizon. Well, we'll prove it's contained in the horizon, but that's a little bit more than I've said so far. Now, this might puzzle you at first, because from each of the Qi, there was a causal path that reaches the world line of the observer at infinity, and these paths have a limit. Does that prove that also from Q you can communicate with infinity? Well, you see, the gamma I I said they were paths from qi to I, but we could think of them as paths from qi to some points pi in I. So let's label these points P1, P2, P3, and so on. If the points qi have a limit, namely q, if the points pi would have a limit, then we actually would have a contradiction, because then the gamma I would have to converge to a path from q to p. So the pi have no limit, since if pi would converge to some point in the orbit, then gamma would be a path from q to that point. The way for the pi not to have a limit is that they're farther and farther in the future. So as the initial point, the q's, approach the horizon, from each of the points outside the horizon, you can communicate with the observer at infinity, but the moment at which the signal arrives is later and later as you approach the horizon. And in the limit that you reach q, the limiting causal curve exists, but it never gets to the world line I. As you probably all know from a more elementary course in general relativity, that's the situation for the idealized Schwarzschild solution. Let's just draw it again. Here's the world line I. Here are the points outside the horizon, Q1, Q2, Q3. From each of these, we can communicate with the observer at infinity, but the signal arrives later and later. And from the horizon, there's a limiting path, still at a pi/4 angle from the vertical in that picture, but it never gets to the observer at infinity. It reaches at this point, which is at t equals plus infinity. So what we've proved here is that what happens in the idealized Schwarzschild solution is generic. As long as you're outside the horizon, you can communicate with infinity, but as you approach the horizon, the time at which a signal you emit reaches infinity goes to infinity. Any questions?
Did we already see that the horizon was lifelike?
No, we haven't quite seen it yet. That's what we're about to see.
Okay, good.
So this curve gamma from Q has the following properties. One is that it can never leave the black hole region as it is a causal curve from a point in the black hole region. The second fact is it can never be in the interior of the black hole region as it is a limit of curves outside the black hole region. See, the curves M are strictly outside the black hole region. Sorry, the curves gamma I are strictly outside the black hole region, and they have a limit gamma which is in the black hole region. But the limit curve has to be in the boundary of the black hole region, not in the interior. A sequence of curves that are strictly outside the black hole region can have a limit on the boundary of the black hole region, but not a limit inside the black hole region. So putting this together, gamma is entirely contained in the boundary of the black hole region, which is, by definition, the horizon. So, again, that generalizes what we see in the idealized solution. In the idealized solution, we see that the limiting curve is an outgoing null ray. that remains for all times on the horizon. We've proved that something similar to that is true in general. Questions there? Now, more than that, gamma has to be prompt. Because, you see, I'd like to erase part of this picture so we can see it better. Suppose gamma is non-prompt. That means there's a path, there's a different path, causal path, from Q that arrives a little bit to the past of some point that gamma reaches. So gamma reaches some point R, which is in the horizon. I want to prove that the segment of gamma from Q to R is prompt. For it not to be prompt would mean that there's some other causal path from Q that arrives a little bit in its past. But then the whole future of that point would be in the black hole region. And that would prove that R is in the interior of the black hole region. But we've already decided that R is in the boundary of the black hole region. I hope I managed to state that clearly. I'll try again. We have this distinguished path, causal curve gamma, from Q in the horizon, and let R be some point in the future along gamma. I want to claim that gamma is prompt as a path from Q to R. That means there's no other causal path that would have reached a little bit to the past of R. If there is one, let's say it reaches R prime, which is the past of R. Well, R prime is then in the future of Q, causal future. All points in the future of R prime are in the future of Q. And that would force R to be in the interior of the black hole region, not its boundary. So therefore, gamma is a null geodesic with no focal point. I mean, we proved it was prompt, and we know that a necessary condition for a causal curve to be prompt is that it's a null geodesic without a focal point. Now, in getting this far, we just considered a particular point on the horizon. But now we're going to change tacks a little bit. And we'll pick an initial value surface S, and then S intersect the horizon is going to be some 2 manifold W. And now we're going to think for a moment of causal curves from W. Well, if I pick any point Q on W, I can say the same thing as before. We constructed for each Q a prompt null geodesic gamma Q, I'll call it now, emanating from Q and staying always on the horizon. If I take another point Q prime on the horizon, or on W, the same construction applies. The problem is just how to draw it in a two-dimensional flat blackboard, but the same construction applies, and there will be a curve gamma Q prime emanating from Q prime, also a prompt null geodesic. Now, so far, what I've proved is that these gamma Q is prompt as a curve from Q, and gamma Q prime is prompt as a curve from Q prime. But actually, a stronger statement is true. Gamma q is prompt not just from q, but from w. In other words, if you to say that gamma q is prompt from q means that if you deform gamma q as a causal curve, keeping fixed the initial point q, you can't make it arrive sooner. Saying it's prompt from w would mean that even if you change the initial point, let's say you start from here, nearby, you can't arrive sooner. Well, even changing the initial point, if you could arrive sooner, we'd get the same contradiction as before. We'd prove that this point is in the interior of the black hole region. So essentially the same argument as before shows that these null curves that emanate from horizon points and stay in the horizon are prompt as curves from W, not just as curves from wherever they originate. So that gives us, so we have one more property of gamma now. It's a null geodesic with no focal points, and it's orthogonal to W. So we've learned that the horizon is swept out by a family of prompt null geodesics that originate from W. You see, as a preliminary before we proved Penrose's theorem, we discussed, a couple lectures ago, we discussed a hypersurface Y that was swept out by orthogonal null geodesics from a codimension 2 space-like surface W. We discussed this as a preliminary for explaining Raychaudhuri's equation. And we found the metric of Y could be put in this form. Well, first of all, Y can be parameterized by XA, which were coordinates on W, and U, which was an affine parameter along the geodesics. We found then that the canonical form of the metric was 0 times du squared plus 0 times du dxa plus something that depends on both x and u times dxa dxb. So we introduced such a y as a step toward understanding Raychaudhuri's equation, but now we know that the horizon is such a y. In other words, H, the horizon looks like what I've described over here. Now, something which is true here, but which I didn't discuss when we were discussing Raychaudhuri's equation, is the following. In constructing this, remember in discussing Raychaudhuri's equation, we did something more complicated. We also introduced V, where this manifold is V equals 0, and we had a metric on the whole spacetime. Today we're not talking about that. We're just looking at the metric of Y. So in comparing to the previous lecture, V is 0. And we see that this metric is null. The horizon has signature plus plus 0. And it has an interesting property. I'll just write the metric again. In this setup, W was U equals 0. But we could define some more general W, I'll call it WF, by U equals what I call F of the x's. People call that a cut of the horizon. And this metric has the following property. The curves xa equals constant are orthogonal to the W we started with, but they're orthogonal to any horizon cut. In fact, we could change variables to U tilde, which is U minus F of the x's. And this metric would remain in the same form with a different function g. The metric would just now be g tilde AB of x and U tilde times dx dx. So there's complete democracy among all horizon cuts. We picked a particular horizon cut to deduce that the horizon was swept out by these prompt null geodesics, but once we knew that, we have the metric in this form, and it shows us that any other horizon cut would have led to a metric of the same kind. So the intrinsic way to say it without, okay, there's a very, okay. So the horizon is a null hypersurface that's swept out by prompt null geodesics. There is some redundancy in that description. You can prove that it's enough to know that the horizon is a null hypersurface. There's a very surprising fact about Lorentz signature geometry. A null hypersurface is always swept out by null geodesics. I don't think that's obvious. There's a proof in an appendix in my article. I'm not planning to explain it in this course, in the lectures. So if you want to know the converse, you'll have to look there or someplace else. It's not in Wold's book, but anyway, it is in, I did write an appendix about it. Anyway, the facts you want to understand about the horizon are that it's a null hypersurface and it's swept out by these prompt null geodesics, which are called horizon generators. So the orthogonal null geodesics gamma that sweep out the horizon, and they're orthogonal to any cut. We started with a particular cut in order to define them, but then we discovered they were orthogonal to any cut. They're called horizon generators. Any questions on the horizon generators? Okay. So there's one remaining result that we still have to explain, and that's the most important fact. We'll start talking about it today, but we'll have to continue next time because we only have 5 minutes. So the last and particularly important result, is the Hawking area theorem. So here's a schematic picture of the horizon swept out by orthogonal null geodesics from a codimension 2 surface W. And we could consider, and then we could look at another W later on. So W and W prime are two different horizon cuts with W to the future of W prime to the future of W. So they have areas. There's a metric GAB of x and u, which we evaluate at u equals 0 for w and at u equals f for w prime. And then we have the area element, which is the square root of the determinant of g at 0, and a prime is the square root of the determinant of g at u equals f. And then the areas are the integrated area elements. I guess I should call it integral over d minus 2 because we're in d dimensions. The Hawking area theorem says that A prime is equal to or bigger than A. But it's deduced from the following. If we let theta of x and u be 1 over a dua, then theta of x and u is everywhere non-negative. So, if you know this, then integrating it implies that the derivative of the area as you go toward the future is non-negative. In the motivating example of Schwarzschild, the horizon is at r equals 2 gm, and the area of a horizon cut is 4 pi times 2 gm squared for any cut. So in the motivating example of Schwarzschild, the Hawking area theorem is actually an equality, not an inequality. The intuition of Penrose and Hawking was that if you throw in matter, the black hole mass gets bigger, so you can make the area increase. But there's no obvious way to make the area decrease. I should mention something that was known at the time of Hawking's work on this theorem. You might have thought more naively the black hole energy could only increase. That's actually false. Penrose had shown that in the case of a rotating black hole, if you send in matter with opposite angular momentum, you can reduce the angular momentum of the black hole and actually reduce the black hole energy. And similarly, in the case of an electrically charged black hole, if you send in particles with the opposite charge, you can reduce the black hole energy. Christodoulou, who I think was a student of Wheeler's here at Princeton at the time, investigated these phenomena and showed that there was something that can only increase in all those processes. I don't think Christodoulou, as far as I know, interpreted it as the area, but Penrose and Hawking did, And Hawking proved that the area could only increase. And he proved it by showing that the expansion on the horizon is everywhere non-negative. So that shows that if you follow any one of these null geodesics into the future, the local area density is increasing, or at least not decreasing. The total black hole area might increase by more than that, because, for example, new black holes might form, but more subtly, although harder to explain. You see, these horizon generators are future complete, but they're not past complete. We only follow them toward the future. So as you go to a later cut, see, if you compare one cut to another, all the horizon generators that existed on the earlier cut will exist on the later cut, because we prove they keep roughly. We'll prove it more completely in the next lecture, but roughly we prove that they go as long as the space-time does. But there could be horizon generators on S prime that don't come from anything on S. An obvious way that could happen is this. At some intervening time, S double prime, a new black hole forms. So there are new horizon generators that obviously have nothing to do with what was for this black hole. But then in between this, before we get to S prime, the two black holes can merge. So in that way, you end up with a single black hole, but it has horizon generators that didn't emerge from anything on S. However, in the proof of the Hawking area theorem, you show that just the horizon generators you know about are enough to ensure that the area can only increase. It might increase by more than you predict on this basis, but it can't increase by less. But in view of the time, we'll discuss the proof on Thursday. And then we'll go on to other things like topological censorship. So on Thursday, we'll also start to discuss the next section in the lecture notes for those of you who are looking at those lecture notes. Any questions, briefly?
If we have a wormhole, do we have black hole region?
What did you ask?
If we have wormhole,
Yes.
do we have black hole region?
Yes. We have said nothing today that assumed there was no wormholes. And we will analyze wormholes on Thursday. But we made no assumption today about the topology of space, except that there was an asymptotically flat region. We didn't assume there was only one asymptotically flat region. We assumed that there was an asymptotically flat region where the observer lived, and we studied what that observer could see. Any other questions? Yes?
Did we use an energy condition somewhere?
We did because we used the fact that a null geodesic couldn't be prompt for indefinitely. So that uses the null energy condition. We use this. We use the same fact Penrose had used, but we just use them differently. We use the fact that the we use the fact that null geodesics. Our main starting point was to say that a trapped surface is in the black hole region. To prove that, we use the fact that orthogonal null geodesics from the trapped surface can't remain prompt indefinitely. We had an upper bound on how much affine parameter space they can be prompt for. And that is the same argument that went into Penrose's theorem. It uses the null energy condition. Any other questions? Okay, I'll see you Thursday and we'll discuss the area theorem.
I'm not sure.